All right, so learning with logical constraints. I found this to be a really interesting topic because, you tend to think of things like multi-label classification as kind of a solved problem, right? There's like probably things in scikit-learn that claim to do this. But when you think about it, once you start adding any kind of constraint, stuff gets a lot harder very quickly. And so, in some ways, we've already started this lesson when we talked about abductive learning, because by having a logic program that the results must conform to, that is a form of adding a logical constraint. And we can think of the logic in abductive learning as, maybe overkill for like a multi-class classification type problem. But maybe that's where things need to go anyway. Maybe we need to just be able to put arbitrary knowledge that the results have to align to. So there's various approaches. So one is loss-based, that often will use fuzzy logic. And the idea here is the results of the machine learning model has to be close to satisfying the constraints, but doesn't necessarily have to satisfy them. Because normally here there's an additional term in the loss function that is dealing with level of consistency in addition to your normal mean squared error or cross entropy. And again, we saw this kind of thing going on with abductive learning, right? But I kind of view this as kind of one way of doing business, and it's closely coupled with the use of fuzzy logic, because you can have fuzzy levels of satisfaction, and the two often appear together. So today we will talk about logic tensor networks. There are some other approaches that are similar, such as semantic loss, logical neural networks kind of falls in here, but we picked LTN because it's, probably one of the more established approaches. So next is the replacement of the outer layer. So this approach deals with, hey, you have, if you have a bunch of mutually exclusive things, you have a softmax layer. If the things that you're concluding about the data are not mutually exclusive, there's going to be sigmoid, or maybe there's like, blocks of softmax that are separate, because each of those things you're trying to determine one of the labels. And the idea here is, let's just replace that with something else that doesn't have a lot of implicit assumptions. And we're going to kind of learn what those correlations are. And in the same framework, we can also add in additional constraints. And these would be hard constraints in the neural architecture, which is actually a really interesting thing. So I'm going to cover SPL, basically because this leverages probabilistic circuits, which is, I think, something worth exposing you all to. I think it's an interesting way to do business. A related approach out of the group out of Vienna, hierarchical multi-class CNNs. But the one issue is with this is they kind of tied this to images only, where SPL, they present it more as a generalized method. So we'll cover that. So then I think there's a sort of another way to think about things is neural error correction of labels, okay? So with ABL, we did correction of labels, but it was being done with a symbolic process. And so this is a fairly new paper that I haven't seen anything else like it yet, called NASR. And here, what they're doing is they're actually using a transformer model to learn a mask over the answer to the neural model. And then they're using the symbolic algorithms to fill in the stuff that was masked. And they're training the neural model to learn things that are wrong in the answer. Okay, so that's kind of, I thought that was a really interesting approach. And then on the other hand, we have a symbolic error correction of labels. So here, ABL, I think, falls into this category. But we're going to talk today about STLNet, which is a bit different approach. It does not involve abductive inference, and this involves this notion of having a parent-teacher paradigm for training the network. So let's start with LTMs. So I'm going to go through the formalism because it's a little bit involved. And so they have this notion of a domain. And so a domain for the constants in the logical language, domains are different, like almost like a data type. And the reason why they have different domains for constants, which is not something typically you see if you look in a pure logic paper, is because they're looking for these constants to be produced from the neural model. And the shape of the tensor representation for data of different types may be different. So you might have like, some sound that is one shape of a tensor. You may have an image that's a different shape and so on. And so a grounding assigns a constant symbol to a tensor. So this is a little bit different than other uses of the word grounding. So if you look at, traditionally with grounding symbols, you think of going the other way around. And also this differs from the notion and logic of grounding stuff from a first order logic statement with variables to one that only has constants. But for purposes of this discussion, we'll kind of go with, their G function there, and it takes in a constant symbol and it gives you a tensor. Variables, are also associated with the domain. So I can use a variable symbol, and the reason why you want to do this is because if you have domains for constants, you want to have the right data type going with that variable symbol. So they have that, and the idea here is they take the tensor for a constant, and they can represent a variable by adding an additional dimension to that tensor that has one position for every possible constant value encountered. And finally, function symbols over constants and variables. And, and the way this works is you're essentially just applying the function element-wise to the tensor. Okay, so really simple. Predicates are applied to constants as normal. And the grounding of a predicate symbol when it is applied to a single constant is just a scalar in the interval 0, 1. So if you have a totally ground formula in the LTN paradigm, it's being mapped to a single scalar. And the reason for this is simple because they want to use the syntax of fuzzy logic. And in fuzzy logic, all ground atoms map to something in 0, 1. Okay. Also, not a probability. All right. So just please keep that in mind. Not a probability. So to give example, we have an MNIST image. Okay, that one right there. And this image is represented by a tensor of dimensions 256 by 256 by 3. The dimensions of the image. So if we consider a single number 8, not the image of 8, this is represented by a single tensor of 9 by 1. Okay? So the predicate is digit xy. If we say we have an MNIST image as x, and we have a number of this domain as y, once this is grounded, it's going to return something in the unit interval, and you have something like this. Is digit, this MNIST image, an 8, and you want it to map to 0, 1. Yeah?
Shouldn't that be 10 by 1, or is it like because the number is 8, it's 9?
So these are single digits.
The tensor size.
Oh, the tensor size, yes, you're right, that is a type. Thank you. Okay, so if we suppose there are 7 MNIST digits, and if we have a variable x, it's going to give us a vector of length we're going to get a vector of length 7, because now we have to account for all the different input images that X is associated with, okay? And each of these is going to be a scalar between 0 or 1, giving it, the confidence of how much it looks like an 8. So, this is ungrounded with respect to the results of perception. I don't think I need to say anything more than that. All right, to give a little example, we have the grounding. Here is your input tensor for X. Here's your input tensor for the second input. And function f is applied to that. So now the result of the function f, and these are our variable symbols, is going to be, you are going to now consider both x and y dimensions, because you have two ungrounded variables. And then if we add a predicate to that, you still have a square, because here the predicate is applied to two ungrounded variables. All right, so this is producing an ungrounded result. Now, what you could look at is, you could think of looking at the output of this as sort of all possibilities of what P of X comma F of X, Y could be in the output of layer of the network. And you can directly interpret those positions of this matrix as level of truth for each of those. Now, of course, because it's fuzzy logic, when you have that, you can start doing operations over matrices like the one I just showed you. And you have each logical operator can be associated with a function. And typically you have what's called a T-norm for a conjunction, a T conorm for disjunction, and you have fuzzy variants of things like implication and negation. And there's also a whole bunch of different ways to do quantifiers as well. Now, here's the thing. It's an engineering decision to determine which of these functions to use. I think I have. Yeah, so here's some examples of, different functions. You have, Gödel, Lukashevitz, and, product and so forth. So all of these have different properties. If you look at some of the papers on LTN and even some of the older papers on fuzzy logic, a lot of arguments are around, hey, if we define T-norm this way, it has these properties that are more like a conjunction, these other properties that are less so, and so on. There are additional considerations with LTN where you also have to consider how well behaved these are during gradient descent. And if they have issues like vanishing gradient or exploding gradient and so forth, then it causes the training process to stop. Because remember, all of these things end up being part of the loss function in the neural network, okay? Because it's a loss-based approach. So one more quick example. Here we have grounding of X, grounding of Y, and now we're applying predicates P and Q. And notice you still have, these are vectors instead of single values. And then we result here again with a conjunction of it now in 2 dimensions. We have P of X and Q of Y. It's dimensions X, Y, with those being variables. So let's talk about some actual use cases of this and how it's been employed. And we'll start with a simple example, this sort of friendship thing. And here we have, example where the grounding of Mary is, this set of features in that vector. And then the predicate of G being a friend is going to be something, of course, that maps to 0, 1. And now we can look at for all X, where John is a friend of X, then X is also a friend of Mary. And you can kind of work through these where you can, come up with a fuzzy output just by using the functions. When you start adding quantifiers, quantifiers have the effect of cutting down the dimensions of ungrounded statements because they're effectively grounding out one of the symbols. So just like, our other examples where we go through all this stuff, we get to the conjunction, and here we have R, X, Y, and A of Y. This ends up being dimensions of X and Y because those are your two free variables. Now, if we add existential quantifier, there exists Y, we lose a whole dimension, okay? And depending on which function they use for that existential operator dictates the value that's going to be in it. But, you could think of this as if this was all zeros and ones, okay? One thing that, would be existential is just take the max. Because if we were operating classically, you only need one of those guys to be a 1 for the existential, right? And that addresses that. And then likewise, you have for all. And this would be doing something similar. So if we were doing classically, all of those would have to be 1s. Now, of course, when you get to fuzzy, well, what happens if 1's a 0.9 and 1's a 0.7? The way to address this, again, is with the functions that, I showed on the earlier slide. And which one do you choose? Well, a lot of that, I think, is empirical, quite frankly, or dealing with, the properties they have with respect to the optimization process. And I'll just skip this. This is pretty much getting the same point as the previous one. Or actually, no, the reason I put this up here is this is showing for the problem on the next slide of recognizing flowers. How many of you have seen the iris data set? Yeah, like in all intro to machine learning classes. And so they come up with where they're looking at this, where they use conjunction and two quantifiers to make a determination. And looking at how we set this up is your domain. You have, classes of different types of flowers. You have the variables, one for each of the different class types, constants for the class names, predicates. But here's kind of the key thing. Here are your axioms, okay? For all A, P, XA, LA, and so on. All right, so this is setting the constraints up. And here is the loss function. They're using, how well everything is satisfied as part of the loss. Or no, so actually this was the architecture of that. Yeah. Talk about results. They go over results for accuracy overall, and then they also look at what happens with satisfaction of the constraints, which also increases over time. And of course, we would expect this during training because this is what they're optimizing toward. What's interesting here is they used the satisfaction of constraints. There was no loss term in this for cross entropy or anything like that. And so they were still able to get good accuracy despite only looking at how the constraints were satisfied in the problem. Another problem dealt with classifying images of crabs based on classifying crabs based on morphological features. And so they have constraints dealing with, if the crab is classified as a blue crab, then it's not going to be orange. If the crab is blue, then it's not male, so forth. what was interesting here is, so they did the same kind of thing where they looked at the accuracy and level of satisfaction of the constraints, but they also did queries of the data. And they wanted to see if these things were true. These were not part of the initial input. And as the training process goes on, they can measure the level of confidence associated with these logical statements. And so they can, doing this based on training data and with a few constraints, not a complete logic program, they can still answer entailment queries in a way which is an interesting artifact of this approach. Now, all that said, again, these are in terms of fuzzy logic. So we would be looking for things that would be hitting extreme values. If you have it providing a confidence score of 0.4 for a given logical statement, there's not really much you can do with that. It's also, I think, an open topic on how interpretable that is on the whole. If you have something like this and it has a certain fuzzy value, I mean, what does it mean? It doesn't mean like a certain fraction of the data set had this quality. It's very difficult to interpret. So things that are good about this, though, I think probably the number one thing is the first order logic. And they go through a lot of pains to make that really clear. And they take good care of looking at issues like grounding and variables and stuff like that. And I think it's kind of a plus and a minus, but you do have a lot of options with different fuzzy operators, for better or for worse. Also, there have been people using this approach. So the code base is a little more mature than like your average paper. So of course, fuzzy logic is not probabilistic. Constraints are not strictly enforced. And also, even though it's using a first order logic, kind of odd, it doesn't allow for true multi-step inference. So you can't have like, things concluded just from the logical part and then, use those to make more statements in kind of the traditional way of doing logical reasoning. Everything has to be spelled out. And so I think that's also a little bit of a shortcoming. There's a loss of flexibility. Other approaches actually do allow for this, one of which is ABL. So anyway, some of these things are addressed with semantic probabilistic layers, but there's things that LTN does, such as first order logic, that to date aren't done by SPL. So this will be an interesting approach though. So they talk about in the paper, they say, well, we're going to call sort of your general sigmoid function outer layer a fully independent layer, because basically it's assuming that the labels are provided independently. So they write out the product. And so, well, why not just replace that layer with something like this, where you're predicting labels Y conditioned on F, which is the neural network, X is the input, and it's going to be dependent on function Q, which is parameterized with data, which is learned from data. And Q is learning correlations between the labels from the data. Okay, so Q is trained as part of the process. And then you have CK, which are hard constraints that get embedded into the network as well. And so you have these two functions and you have a normalization constant. And of course, looking at this, it looks quite terrible because you're summing over all possible combinations of the output labels. So if you have a whole bunch of ground atoms representing output labels, this is going to be intractable, which is a common thing, right? If you look online at Jerry's lecture on Markov logic networks, like they run into this problem and they overcome it basically by sampling, and it still results in scalability issues. But here, they overcome it by restricting what those functions look like. And so they show at the beginning of the paper, and I kind of like this stuff, maybe it's just me. They have some desiderata about things, well, you know, the layer should have all of these things, okay? So, but of course, you know, first order logic's not listed on there, for example, but never mind that. But they do make a good case here, like this is actually, you know, really probabilistic. Okay, so it abides by the probability axiom, so it's a true probabilistic approach. You know, it's expressive in terms of what it can encode. It assures consistency, which this is a big plus. And then they make some cases about, you know, modularity. It also is, they make a good case for it being efficient, but there's limits to that. So the main idea are those two functions, the C and the Q function, are created using what are called probabilistic circuits, which are essentially just these sum product networks. That's a very straightforward thing. And then these sum product networks, they can be weighted and you can build them up in a modular way. And sort of the basic idea here is the Q function is going to be a probabilistic circuit where the parameters, these weights on the sums, they're going to come from the neural network. And the neural network is being used to learn the parameters of the probabilistic circuit that gives the output. The other function, the CK function, that comes from constraints, you have these logical constraints and they're compiled into a probabilistic circuit. So there's two big properties they talk about, smoothness and decomposability. With smoothness, every sum unit depends on the same variables. With decomposability, every product depends on disjoint variables. Now, right away, this should kind of start to look maybe like something we've all seen before, like a Bayesian network maybe. And these properties, you can really think of allowing sort of a local independence within the structure, because if you have smoothness, every sum depends on the same variables. That means you can think about all the inputs to a sum being mutually exclusive, and if you have a bunch of mutually exclusive things with probabilities and you sum them together, getting the disjunction of those different events. Likewise, the product depends on disjoint variables. If you have independence there, you can then take the product of those probabilities and you get a legitimate conjunction because you have this independence. So these properties also give rise to this notion of compatibility that allows these probabilistic circuits to be combined in a modular manner. And that's kind of that plays a big role in allowing you to have both the Q and the C probabilistic circuit together in the same neural architecture. So a probabilistic circuit can model a probability distribution over subsets of labels, and they parameterize it based on this function G, and G is applied to the last layer of the neural network. So remember, we're getting rid of the output layer, so that stuff has to go somewhere. So it goes to this function G. So what is G? Well, G is just, what they just use is a simple multi-layer perceptron, and the output layer of that, the parameters for the sum is done with the softmax layer, and the parameters used for the product are sigmoid. And this makes a lot of sense, right? Because it ensures that, you know, you have this kind of mutual exclusivity and this independence, you know, property there. Okay, so we got function Q. Well, what about C? Well, given a logical constraint, it can be compiled in an ordered binary decision diagram. Now, this is something that's common in the verification community, where you got something like an MDP or a crypt key structure representing a process, and you have a formula, usually in like a temporal logic, like LTL or CTL. And one of the big results in that line of work over the years was, hey, you can take the CTL formula, you can compile it into something like an OBDD, and then that'll allow it to play nice with your crypt key structure. Well, previous work prior to this paper shows that the OBDD can be translated into a probabilistic circuit. Now, the worst case is the size of the OBDD could be exponential in size of the CNF representation of the formula. But the thing is that these methodologies have been around for a long time and have gotten very mature. It's been observed that when you actually do this process, it ends up being much smaller. And so they're taking advantage of these practical implementations. Now, one thing to keep in mind here, though, is because this technique that came out of the work of the verification community, the verification community is really concerned with checking a series of what they call specifications, which are their logical formulas. And if the system abides by that, that's not a logic program. It's just like a bunch of logical sentences that we don't want this behavior to ever occur. And so, my question is, would this scale to do something like what ABL is trying to do, where you actually have a logic program, or what some of that work toward the end of the ABL lecture, where they wanted to, generate a really big logic program out of a knowledge graph? That's where I would start to be doubtful. And I'd also be doubtful is if you wanted to extend this to the first order logic case, you essentially have to be grounding out your first order logic statement into a bunch of formulas. And that would also, we'd start to see increased size and things here. Now, I'm not saying that it wouldn't work or it would necessarily be exponential in size, but it hasn't been shown that this could be done yet. And that could be where the limits of scalability occur. So putting this all together, then they provide a strong theoretical result where this allows for efficient inference, where it's in the size of the Q circuit multiplied by the size of the C circuit is the complexity of it. So if you're looking at only Q is you get to pick how big that is based on how many correlations you want to capture. C comes from your logical formula. And so if you only have a small number of constraints and it doesn't blow up when you do the conversion, this actually ends up being pretty fast. So experiments, so they look at this Warcraft pathfinding experiment where it has to find a path in the game board that has to also be a legitimate path. So finding something like this, which is produced by a sigmoid output layer, doesn't make any sense because you have big gaps in the path. It's not a valid path. Even with semantic loss, they found that it would often not return a valid path. But here, where they're assured of consistency, it has to return a valid path in the solution. And so when you see the results up top, this one trivially gets 100% on consistency. And that's just because it has to. It's just designed that way. It can't violate those constraints. The other thing interesting too, and this comes up in this paper a lot, is this exact match versus Hamming distance. And the Hamming distance basically is giving sort of credit for partial solutions. But what could happen there is you could have all of these paths, or a huge number of the paths in the test set could be off by a little bit, and it could cause this Hamming distance number to be inflated. So even though they don't do as good on that, for exact match they do better, and they're doing actual paths 100% of the time. They did a similar comparison to the HMCNN that I mentioned at the beginning of the lecture, and this primarily has been used in things like medical imagery. Both approaches can guarantee consistency, so they both scored 100% on that. The place where SPL starts to shine is in terms of exact match. It outperforms HMCNN, even though that does better on the Hamming score, but even in this case, SPL is not that far off, usually just 1% or 2% behind on that. And HMCNN at the time of the writing of this paper was state of the art for these tests. So again, I mean, this is really cool because they have a tractable framework that is really probabilistic. Constraints are strictly enforced. So that's really great, especially for task stealing, with robotics and safety and stuff like that. And also not really featured in the experiments, but the output layer is also learning correlations among the output classes at the same time. I don't know, how they could have measured that and shown that empirically as well. But that's kind of an interesting thing. And the whole thing is quite elegant. Like it's very strong theory, implementation reflects the theory, very crisply. And so I think that's great too. It's only propositional though. And no notion of multi-step inference. And we don't know what happens if you go to like a really big logical statements. The other thing is the identified correlations by Q. They're likely not interpretable, which is probably part of the reason they didn't talk about that in the experiments. And the reason for that is you got kind of a mess of parameters going into that Q function that dictates how that that PDF works, and it probably is not anything you can make sense of, I would guess. The other thing too is there's kind of this implicit closed world assumption that goes throughout the whole thing. And honestly, most of the approaches that we're talking about actually have this. LTN has it as well, where if it's not true, it's false. And so that's definitely present here too. All right, so the next one is a really recent paper, Neural Attention for Symbolic Reasoning. Now this differs from a bunch of the previous approaches is it's a much more engineering style solution to the problem. And they even say in the paper, hey, we have these kind of big boxes and you can replace anything with some other kind of approach. It's more at kind of the system level, how these things operate together. So the key intuition is that, if you do inference with a neural network, yeah, it's going to mess a lot of things up, but it's going to do it really fast. And it's going to get a bunch of the pieces of it right, but the whole thing is likely not going to be very good. But what if we can just identify the pieces of the solution that are most likely to be wrong, and then use logic to fill in the rest? Because maybe the neural network just does a good job of, organizing some of the base facts, okay? And so that's the idea. The neural network is actually doing perception and reasoning. And then you're masking the output of the neural network's reasoning, and then you're using inference to correct the things that we're masking. So here's an example they give in the paper. You got, this image, bunch of bounding boxes, different things in the image. And, the neural approach gives you the scene graph. The mask says, hey, these edges we're going to just erase. They're most likely wrong. And then the symbolic solver uses some rules and it fills in those with different edges. So in some ways, the idea is similar to ABL, but with the big difference that you're not using abduction to change the output of the neural model. And also, they're actually using neural models to do reasoning. So they're pushing the neural stuff even further. So you have, I got some animation. So the first piece is a perceptual model. So this is like, the CNN using STLNet or even ABL. And I'll talk bunch about STLNet here because the big thing they do is Sudoku. And then they got the solver neural network, okay? Now they even do an experiment where they use a STLNet solver for the neural network, but they also use an attention-based one that does a little better than STLNet. But it's as if they had looked at the STLNet paper and said, hey, that thing actually does pretty well. And STLNet does result in a neural network, not a symbolic way to solve the problem. Then what you have this mask predictor. This is trained on different data. I'll go over how it's trained in a moment. But this covers up what we think the mistakes are of this model here. And then finally, we have a logical solution that has a bunch of holes in it, these zeros, and those holes get filled in with the logical solution. They make, to the point of modularity, they make a really neat point in that, hey, this guy, this doesn't have to be just like, prologue. It doesn't have to be a first order logic. It could be something like, physics-based differential equations. It could just be standard, mathematics. It could be something coming from a very clean and well-structured database. And I think that's a really neat point. So how is the mask predictor trained? Well, this is what they do, and it seems to work well. They take the ground truth from the original data set. So here they're doing Sudoku again, and they're randomly replacing components of the game board with noise. And then so that is the input data, taking the ground truth with some of these values replaced. And then the ground truth for this data set is the things that are random, those are zeros and everything else is a 1, because you want to mask out the random noise in the answer. And so the idea is this would be kind of a really good detector of things that are incorrect. Now, just as a little refresher on our problem we have here, this is the visual Sudoku, this is the problem they look at. Input looks like this, output looks like that. They use just a standard CNN digit recognition like the LINET variant. They have a transformer for a solver, another transformer for mask prediction. The logic is done in Prolog. And then they also do this reinforcement learning step to refine the interplay between the mask and the symbolic solver. Now, one thing you may notice is this has kind of the label leakage thing. The original STLNet paper does, but here the CNN is already being trained directly on digits. So it's not really a factor in this work. So with the reinforcement learning used to refine things, basically they're looking at the correctness of the board versus as well as the correctness of the individual squares in the board. And this kind of gets to the concept from some of the experiments in the last two papers where you have Hamming distance versus overall accuracy. And kind of the idea here is that, the overall board, this is going to be a harder quantity for reinforcement learning to increase. It's just going to kind of, suddenly go up. But, for a given sample, but each individual square is much more, easy to improve upon. So it gives us something within the iterations that can make these local improvements. So the overall results, they looked at a symbolic baseline. They did the base SatNet. They did STLNet using their approach, Neuro ASP, and then their end-to-end approach. The data sets are kind of interesting. So Big Kaggle is just like a Kaggle thing of Sudoku boards. They did well, the other approaches did all right. Minimal 17, so if you saw on the earlier slide, the input is partially solved Sudoku boards. Minimal 17 only has 17 entries in there. And this is a 9x9 board, so it's extremely sparse. And so this does quite well. And notice that the symbolic solver, Neuro ASP does well, but they couldn't train it very much. They had scalability issues. If you ever saw the video Chitterberl did on Neuro ASP, that's the biggest problem with that, which is why it generally times out. But STLNet and the other baseline, they kind of don't do very well. Same thing goes to multiple solutions. So you can think of those two tests in the middle as being particularly challenging from a symbolic perspective. Then they did a nice little ablation study here where they look at, these are cell-based metrics, these are the entire board, and the impact of doing different things. So here they use some kind of heuristic approach to the mask instead of the neural model. They look at what happens without reinforcement learning and with reinforcement learning. And we see the biggest difference reinforcement learning adds are in the more difficult symbolic tasks. Because I think what's going on there is the mask is trained only on these kind of randomly replaced cells in the board, where the reinforcement learning is taking the feedback from the symbolic solver and going back and refining the mask. And so that feedback, I think, is allowing it to generalize a lot more, I think is what's happening there. So, again, I like that the components are very distinct. It's not changing the perceptual model, but rather identifying, and actually this is slightly incorrect, it's identifying where the reasoning module makes mistakes. Although that said, I don't think there'd be anything that would prevent you from using this in the same way as ABL, directly on perception. The logic doesn't need to be differentiable, so that's kind of a plus. And Sudoku it's a much more challenging than the benchmark seen in the ABL work. But that said, it is only Sudoku, so there's some limits there to the evaluation. But this is also a very recent paper, only a few months ago. All right, so we do have a little bit of time. I'll quickly go through STLNet. So I'm not gonna talk about temporal logic, in great detail, but just know that the temporal logic formula, it's going to be, you have an output that is a sequence of things, and we want to check if that sequence satisfies the temporal logic formula. So the additional operators allow you to judge, something at time 1 versus time 3, if those go together and so forth. So you have these n times, you have sequences of m variables over m time steps. And then they have prefixes and suffixes, where the prefix is basically your input sample, and you want your model to generate like some kind of output. So think transformers and recurrent neural nets. And so, so this is the output goes from positions, goes from position I+1 to n for each sample. And F is your neural function that takes in the first I positions of the sequence as input. So we have some properties that we want to satisfy. These are our temporal formulas. Temporal logic formulas, and STL is what they use. And the idea is you want to find the parameters for the model that minimizes loss such that the output of the model satisfies the constraints. And yeah, they use D as distance function, part of the loss, L2. So this is just an example of some of the different types of temporal constraints. They actually have logic here. But these are all things like, there should be at least one patrol car around the school every day. So if there's like a scheduling problem, and these safety issues, there will be certain requirements you have to do, have minimum things. In business world, you have things like SLAs that companies have to abide by. So if you're doing things in an automated way, you need to make sure those are adhered to. So we have the student network is the basic neural network. That's the thing that is predicting the output sequence. What they call a teacher network is actually more of an algorithm. What it does here is it's taking the output of the neural network and it is effectively correcting. In some ways, that's similar to the idea behind ABL. But it's not doing it with abduction. It's more of a deductive process. Then they're using a special loss function applied to the student network that is a little bit different than what we've seen in the past, where the loss function considers accuracy, but it also considers how close the output is to the result of the teacher network. And you iterate between the last two steps until the results of both the student and the teacher look the same or close to each other. And so this is that loss function I tell you about. You have hyperparameter B. It's a number between 0 and 1. This is your standard loss. And this is a comparison between the teacher results and the student. That is weighted with 1 minus beta. So what's interesting is you get two results. So you get the student result, which is going to more accurately represent the data. But you'll get the teacher result, which is guaranteed to meet all the constraints. And I think that's what's, that's one of the main reasons I wanted to talk about this one, because, we've seen several approaches now where sometimes you have kind of a fuzzy version of consistency, and sometimes you have very strict. Well, this approach gives you both, and you can just pick which one based on your needs. And so here's the main idea. Again, they show an RNN, takes the input. Then the teacher network is going through, is doing this thing called a trace generator that is taking in as input the formulas and using that to replace parts of the output of the student network. And that's how it completes the loop. Adjusting the result. So we'll talk a bit about how they go through this process. So the first idea is converting the specification to disjunctive normal form. Now this is where we have some of the same questions that I had about SPL. Because in the experiments here, they generally looked at constraints that are where the logical formula is very small. Well, converting to DNF, you could potentially have an exponential log. And so there remains an open question of this approach can actually scale. So the idea here is that if you, by converting it to this DNF form, you essentially have, a sort of a state or a world associated with each time point. And based on that, you can now do a direct comparison with the output of the neural network, and you could just easily replace the minimal number of symbols to make it correct. So then they talk about how the formulas have an associated DNF representation, and they provide an algorithm to do so. And so results on generated data. They looked at generated sequences, both LSTM and transformer. And they look at, this is the P and Q, where Q is the teacher and P is the student. And so you see satisfaction rate, is not at 100%. But in general, you're looking at higher satisfaction rates with the student network than with the baseline approach that doesn't do anything to address consistency. Likewise, satisfaction rate here is, at 100%, because again, they're guaranteed that result with the teacher network. Another shortcoming of this paper is beyond simulated study. Results are a little limited. They did have one data set on air quality prediction, and they look at, results here for, the prediction length, satisfaction rate, and so on. But again, it's, I think STLNet probably would need a lot more verification empirically and a lot more examination of things like, what is the role of the hyperparameter? How sensitive are these results to the hyperparameter beta that does the trade-off between consistency and accuracy? Also, how does this scale in practice in terms of larger logical formula? And those remain open questions. So just a couple concluding remarks. There's some broad commonality, so we could see some of the approaches deal with different ways to correct errors in the output of the neural model. Some approaches, function by adding a layer, and then of course we have fuzzy and loss-based kind of stuff, which the two don't necessarily have to be the same thing as well. We also look at some other ways to characterize, such as, which approaches require some sort of conversion process on the constraints, which require the logic to be differentiable, and where does that not matter anymore? And then I think some, bigger themes, and you probably have seen, you probably have kind of got this by now, constraints versus logic program. And I think that's a really big difference depending on what you're trying to do. If you are looking to do something like a puzzle that's being solved where there's a whole bunch of rules and there's step-by-step things, you're probably going to want something that accepts programs. You're probably not going to want to engage with an approach for constraints. Now that said, if you're dealing with a problem and it's just a very straightforward multi-class labeling problem, maybe you don't need that extra overhead of having a full-fledged symbolic solver, and something like SPL or HMCNN is going to give you great results. Similar arguments on first order versus propositional logic. And propositional, I think, is most useful, again, in the case where they're looking to go just beyond the standard, multi-class label problem. Where first order logic, if you start getting involved with things like graphical structures, that becomes more important. The same kind of thinking goes in terms of you need inference steps to actually solve the problem. Inference steps really comes into play when does the logic need to conclude some intermediate latent thing that was not present in the training data at all in order to make the right solution. And maybe I need to know something about that intermediate thing. And so you could think of, if I'm observing an airplane doing something and I want to, I can make inferences on what that's going to do based on the way the pilot's controlling the system. I can't observe that from a distance, but maybe I can, fit the behaviors to those actions based on what I know about that domain. And so anything where there's that kind of latent stuff, you probably want to think about using inference steps.